Let's look at this graphically. Say we have some interval a to b, and we'll say that this point here is our a f of a, and then we'll say like up here we have a point b f of b. Okay, so if we have some value k, let's call this k, in between f of a and f of b. Now if this function is continuous on the interval a to b, do you see that it would have to cross the y value of k somewhere, right? So if we had something like maybe a discontinuous function, we could have it go like this or something. It could skip over that y value, right? But if we make sure that the function is continuous, or that is, if we know the function is continuous, any y value or any intermediate value between f of a and f of b, somewhere this function will have to cross that y value. Or in other words, there will be some c value where f of c is equal to k. So again, the key condition, well, there's two conditions, but the key condition here, first of all, is f is continuous on a closed interval ab, and secondly, k is a number between f of a and f of b. So these are the two conditions. Suppose both of these are true. Then our conclusion would be there is a value c in the open interval ab such that f of c is equal to k. So again, if it's continuous, you can see that in order to go from this point to this point, if you have a continuous function, it's going to have to cross every single y value in between f of a and f of b. It's going to have to cross every intermediate value between f of a and f of b. And now we don't know anything about values outside of f of a or f of b, so we don't know that it could go something like this, right? And it could hit values like, say, greater than f of b, or it could go like this and hit y values below f of a. But just in terms of just knowing that this is continuous, we can guarantee that it definitely hits all the y values in between f of a and f of b. So again, there will be some x value, some c value in this open interval ab where f of c will be equal to that k value. Now a typical application of this theorem would be determining if you have a zero or a root of a function. So first of all, we have this whole expression would be a polynomial, right? So if we say, if we look at like f of x equal to that left side, x to the fourth plus 2x cubed minus 5x squared minus 3 is a polynomial. That's going to be, if it's a polynomial, we know it is continuous everywhere, right? F of x is a polynomial and therefore continuous. On the interval, actually it's continuous everywhere, but more specifically we'll say on the interval 1 to 2. To use the intermediate value theorem, we have to have a function that's continuous on the closed interval, and then we're going to check the function values at the endpoints. Okay, so we're going to find f of 1, and that would be what, 1 to the fourth. There's 1, 2 times 1, or 2, minus 5 times 1 squared, or 5, minus 3. This is going to be, what, 3 minus 3 would be 0, or this is going to be negative 5. And then we're going to want to find f of 2. So f of 2, we're going to have 2 to the fourth plus 2 times 2 cubed, or actually that's going to be 2 to the fourth again, minus 5 times 2 squared, or 4, and then minus 3, so this is going to be, what, 16 plus 16 minus 20 minus 3, and 32 minus 20 is going to be, what, 12 minus 3, or 9. So this is going to be greater than 0. The other one was less than 0, right? And we want to see if this thing equals 0, somewhere in between 1 and 2. So we have our function value at negative 5 when x equals 1, and our function value at positive 9 when x equals 2. So you have a situation where it's down here at negative 5. Let's say this is negative 5. And let's just say this won't be to scale, but we'll say this is 9. So from 1 to 2, you have, it's going to have to cross somewhere in between there because it's continuous. So we could say, first of all, let's just say so this is the first condition here, that we have a continuous function on 1, 2, and then here we can say this is our value k. That's going to be between our f of 1 and f of 2. F of 1 is negative, f of 2 is positive, so we're going to have, this is our second condition, so we can say by the intermediate value theorem, there is a value c in the open interval 1, 2, such that f of c is equal to 0, and we can say, therefore, there is a solution to this equation. So, yeah, this would be a typical use for intermediate value theorem. Again, you're just looking for, it doesn't necessarily have to be 0, though. It could be any k value between your f of a and f of b. So it can be used in other cases, but I'm just saying that that's the typical use for it. So remember the two conditions. Your function needs to be continuous on the closed interval, and this number k has to be between f of a, f of b. This is a number that's an intermediate value between f of a and f of b, thus the name intermediate value theorem. The k is an intermediate value. It actually, every y value between f of a and f of b will be somewhere on this function if we have a continuous function, and there will be some x coordinate, some c, at least one c. You remember, you could have more than one c, but this just guarantees there at least one. So, you could have something that goes like this or whatever, and you could have multiples. Like here, you have multiple points where it would hit the k value in that case. But again, the theorem is just going to guarantee that there's at least one anyway. Okay. And don't forget to subscribe to my channel. Just hit the button right over here. Thank you.